Determine the limit of x squared as x tends to 1, and then prove this using the epsilon delta definition for limits. All right, well, x squared is continuous, so if I just plug in 1, 1 squared should be 1. So 1 is likely the limit. But we're being asked to prove this specifically with an epsilon delta style proof. Okay, so we claim the limit is equal to 1. Okay, what do we need to show? What's the epsilon delta style proof that they're looking for? Well, we need to show that no matter what epsilon we choose, we can find a delta so that as long as x's are close enough to 1, this should imply that x squared is close enough in value to its limit 1. At least this is what we claim. Maybe we can't do this and we find that 1 isn't the limit. It will be, but that's something that you should occasionally worry about. Okay? Is there an actual formal proof to back up the things that I know, the things that I'm claiming? Okay. Now, when it comes to constants and linear polynomials, I find epsilon delta proofs tend to be fairly straightforward. But as soon as we move into things like quadratics, cubics, we have to be a bit more careful. Let's try and play around with this. Okay? Now, when I see x squared minus 1, okay, this is the conclusion I want. X squared minus 1, I think, well, I could factor this. And you know what? This is fantastic because I need to start by assuming x minus 1 is small enough, okay, is less than a certain value. So seeing this x minus 1 here gives me hope. But, well, absolute value of x plus 1? I don't get to control that. Okay, remember, when we're doing an epsilon delta proof, somebody hands you an epsilon, you propose a delta, and you show that just assuming this condition, you can figure out this following condition. Okay? So the only thing you can control is this choice of delta. And then you got to go from one statement to another. So I don't get to pick a delta that also governs x plus 1, at least not explicitly. What can we do? Well, one thing we can try and do, let's just explore x plus 1 in absolute value here. Okay. I could get out an x minus 1 from here. Right? That seems nice. Now, is there a way to just split this up? Well, unfortunately, absolute values don't distribute over addition. And that's not a guaranteed thing. Think about something like 8 plus negative 5. We know the answer is 3, but if you try and split it up, you'll get a sum of 13. Those are not the same thing. Okay, but I'll tell you what we can do. We can split this up at a bit of a cost. Okay. So we're going to use our good friend, the triangle inequality. So if you don't remember the triangle inequality, here it is. The absolute value of a sum is always less than or equal to the sum of the absolute values. Okay? Unlike multiplication and division, it's not a clean equality. Okay, so I can do something like this. Right, now how does this help? Well, once again, I can control x minus 1. Right? I can control how big that is. Okay, it's going to be delta, right? So you might say, well, okay, this is going to be less than delta plus 2. And now we've got some sort of control over x plus 1. Okay, so if we go back to x squared minus 1 less than epsilon, we can say, well, this is going to be, this part here is less than delta, this part here is less than delta plus 2. So as long as I pick my delta, so that delta times delta plus 2 fits in between these two, I'll have shown what I need to show. Unfortunately, that now requires me to solve for delta values that sit in here. And that is certainly a possible approach. It's not necessarily going to be the nicest thing. It might only work for some epsilons. For example, if I pick an epsilon value of 1, I need delta squareds to be less than -1. So it's not going to work all the time. It can work for big epsilons, but not for all of them. So while it might be a good observation, we have to do a little more digging. Okay. But I have found a way to control absolute value of x plus 1 by relating it back to x minus 1, which again is the only thing I have control over. All I can do is pick a delta that minimizes, that sort of shrinks, forces, confines the x minus 1. Okay. So let me show you a general trick. You may not have seen this before, or maybe you have, okay, depending on what questions you've looked at. Here's what we're going to do. Okay. I'm going to say, let delta be the minimum between some number, we'll call it 1, and something else to be determined. Okay. So it's a classic trick. Now, why are we going to do this? Okay, why are we doing this? Well, if I do that, I know x minus 1 in absolute value needs to be less than delta, but if delta is the minimum of these two values, I can definitely say that delta is less than or equal to 1. How does this help me? Okay, well, x plus 1 is now going to be less than or equal to 1 plus 2, 3. Now, there's nothing special about the choice of 1. 1 just happens to be the common way to use this. Okay. So as long as I phrase my delta as something like this, I now have control over the absolute value of x plus 1. I have shown that it's going to be less than or equal to 3. Okay. So, assuming that, where can we go from there? Well, x squared minus 1 is what we need to talk about. I know that can split up. Okay, but now this is going to be less than or equal to x minus 1 times the 3, because absolute value of x plus 1 is less than or equal to 3. And I need this to be less than epsilon. I need this to be less than epsilon, so if I make this part less than epsilon, we're all set. Okay. So we need to choose a way to have absolute value of x minus 1 be less than, we'll just bring the 3 over to the other side, epsilon over 3. Okay. So we need this to be satisfied by our choice of delta, but we also need this to be satisfied by our choice of delta. So here's what we're going to do. We're going to let our delta be the minimum of 1 and epsilon over 3. It took us a little while to get there, but that's going to be our delta. But this has all been rough work. Let's actually get to the proper proof. Okay. So let's take an arbitrary epsilon value. So we propose delta should be the minimum of 1 and epsilon over 3. So let's prove this. How are we going to prove it? Well, we start with the only condition we're allowed to have. Suppose, I guess technically I should have had greater than 0 here earlier. Sometimes I forget to do that, but it is part of the epsilon delta definition of a limit. So suppose we have this, delta. Okay. So suppose we have this. Well, we can then see, well, we can ignore the greater than 0 part. That didn't come into it. It doesn't usually come into it with polynomials. Okay. So we can see this is less than delta, and delta is less than or equal to, let's start with 1. Okay. By our construction, we know delta has to be the minimum of these two values. So maybe it's equal to 1, or maybe epsilon over 3 is less than, in which case this is less than 1. Okay. Then we see, and we'll say by triangle inequality, a very common result in absolute values. So we're talking about this x plus 1 because we're thinking ahead. We're going to need this. Okay. We'll say that this is less than or equal to, wow, we'll write it up nice and neat for whoever's reading. Okay. It's less than or equal to absolute value of x minus 1 plus absolute value of 2. I'm just going to skip and say plus 2. So this should be, thanks to this statement here, less than or equal to 1 plus 2 or 3. Okay? So we've got that taken care of. Now, x squared minus 1 is equal to x plus 1 times x minus 1, both in absolute values here, which we just showed is less than or equal to 3 times x minus 1. If you want to, it's always a good idea to number important statements. So this is statement 1, this is statement 2. Okay, or if you don't like using excess numbers, you can use symbols. I like using card suits like diamonds and hearts and clubs and things like that. Okay, so this happens because of statement 2. Okay, and now, thanks to statement 1, okay, because x minus 1 in absolute value is, yes, it's less than 1, but it's also less than epsilon over 3. Okay, well, specifically, we can say, right, because it's less than delta, delta is less than or equal to, so we can say delta. Actually, this isn't statement 1, this is definition of delta. Okay. I want my proof to be nice. Okay, so we'll say less than 3 times delta, which is less than or equal to 3 times epsilon over 3, which is equal to epsilon. There we go. Okay, so what have we got? Okay, absolute value of x squared minus 1 is less than, there's got to be a less than at some point in there, epsilon. Okay, and that's exactly what we wanted to show. Okay. And you'll notice all we did was propose a delta. We started with this assumption, and everything followed from there. Okay, from that and our choice of delta, and we got the conclusion we wanted. So there we go. The limit as x approaches 1 of x squared really is 1.